So, good evening, thank you for coming. Welcome to the final Junior Fellow Lecture Series of this academic year on the theme of contact. I think we've had a really great range of diverse and engaging talks so far this year on topics that not only highlighted the diversity of interests and talents that we have here at Massey, but also highlighted the perhaps rarer talent of being able to broaden or widen one's specific research interest into something that's approachable and welcoming to a wider audience. So I'm honored to be your new co-chair for the Junior Fellow Lecture Series, and I think I have some big shoes to fill because Louis-Philippe and Chris did so seamlessly this year. And I'd really like to thank them and thank the committee for organizing such a stellar program this year. But without further ado, I'm very pleased to introduce tonight's moderator for our final Junior Fellow Lecture Series, Massey's York Fellow Peter McKinnon. Professor McKinnon spent over 2 decades as a lighting designer, primarily for dance and opera. And after that, looking for a career change, he became a general manager and later co-founder of several production companies. And the work in those companies brought him to Broadway, where he later produced a rock musical to great critical acclaim at the Edinburgh Fringe Festival. He's currently working on a 3-volume book that he conceived, manages, and co-edits involving 160 researchers in 64 countries called World Scenography, and it explores stage design worldwide from 1975 to the present. Professor McKinnon has served as president of the Associated Designers of Canada and director of the Canadian Institute for Theatre Technology. He currently sits on the executive committee of the International Organization of Scenographers, Theatre Architects, and Technicians, as well as numerous theatre companies. And in doing some Googling to write this introduction, I learned that his ultimate aspiration is to run a hybrid bookstore and wine bar. And so I think the Junior Fellow Lecture Series held in the Upper Library, wine in hand, is probably a particularly nice opportunity for him to fulfill at least a little slice of that dream. So thank you very much for joining us today.
Thank you very much. So I either have an advantage or a disadvantage in introducing these, which is, and I'm just doing this to make you jealous, I spent the last 2 weeks in the Canal du Midi in the south of France, where I didn't have any internet connection, so I just had to think about contact and what on earth might be meant by contact. And out of the festering heap of my mind, the first thing I thought of was my assistant Oliver when we were doing a show at the Kennedy Center, and we had a big opening night, and what my mother would have described as a fine large evening. And the next day I asked Oliver how he was feeling, and he said he was feeling sort of cheap and tawdry. And I asked what on earth he meant by that, and it's because he had slept with his contacts in all night. But I thought that was unlikely to become the subject of a Massey Junior Fellows lecture. So I began thinking on the boat. I was with my cousin, Jerry, and he had this walking stick, and the rubber tip kept falling off, and he kept buying new ones. And of course, we didn't have the technology to glue one in place. And of course, to replace a rubber tip on a cane or a walking stick, what you really want is contact cement. And I was wondering about contact cement and how that could fit in with the lecture series. And then realized that, of course, as we were going through the canals, every so often, well, twice, and both with large audiences, every so often we would come in contact with the cement of the lock. Now, of course, it wasn't actually cement, it was concrete, but cement is the principal constituent element of concrete, so I can say that we were contacting cement occasionally in the Canal du Midi. And of course, the perfect answer to this is, well, we can't walk through walls. And I thought that this would be much better for someone of Yue Guo's experience and knowledge to answer than a boat driver like me. And she comes to us from McGill and is currently in her 4th year of PhD, which means partway through, most of the way through, some of the way through, depends, right?
Almost done.
Almost done. Oh. Well, my wife took 7 years to get her MA, but she kept saying, all I have to do is write the thesis. and being supervised by Massey's own John Polanyi. and participated in science fairs, of course, as a child, and all the way along, so that now she's still involved with the National Science Fair Foundation, Youth Science Canada, as well as being involved and dedicated in education, youth leadership, etc., on the board of directors of Youth Leadership Development, and is a fan of the Canadiens, and as we know, hockey is a contact sport.
Thank you. So, hello everyone. I thought of talking about something that's a prelude to my research, so I'm not going to go into too much detail into what I actually do. So during my talk, I plan on explaining to you why it is that we cannot walk through walls, and then tell you about the rare times when we actually can, and tell you how that applies in my research. So, unless you're one of these guys, okay, so unless you're one of these guys, you can't walk through walls, right? Like me. You can touch, feel, grab, interact with stuff, precisely because you don't go through them. I mean, that's the whole point of physical contact. The basic premise is that matter doesn't overlap with each other. And when I talk about matter, I mean solid matter, not gas or liquid, because other phenomena are going on there. So the question is, why is it that matter is stable? So first, and this might be really simple for a lot of you scientists here, but let's just recap the most basic component, the building block of matter, which is the atom. So the ancient Greeks and Romans already came up with this concept. So they looked around, they saw the trees, they saw the grass, the sand, and they realized that if you took it and looked at it, it was composed of smaller parts, and even smaller. And so they thought the most indivisible component of matter was something called the atom. And you would have tree atoms, and you would have sand atoms, and different types. And so it was like billiard balls, and just basic round objects that would form larger macroscopic things. And of course, this view survived until the late 1700s. And although there was a lot of progress done in physics and chemistry and understanding how matter worked, the picture was still the same. And then came J.J. Thomson. And so he did an experiment that showed that the atom was in fact not indivisible. There were little subatomic particles in there, and he called those electrons. And these are negatively charged things that were able to move from one atom to another. And so they reviewed the model of the atom, and it became more of a raisin bread model, or the plum pudding model, as they called it back then. And so here you have basically a large mass, and embedded in it are little negatively charged particles called electrons. And the movement of that is what forms electricity and electric current and everything that powers our technology nowadays. And so when you have this picture, then you can imagine thinking that it's still something that's solid, and if you shoot something at this atom, this mass, a few things could happen. If you have something that's not very strong, maybe it'll hit this and bounce off. Or maybe if you shoot a bullet through it, it will pass straight through. And so Ernest Rutherford in the early 1900s did this famous experiment called the gold foil experiment. He took alpha particles, which were positive charges. They're basically the nucleus of a helium atom, so 2 protons and 2 neutrons. And he shot those at a foil of gold. And what he saw was really quite unexpected. Instead of having a uniform behavior of everything going through or not, he saw that lots of things were deflected. So instead of seeing one path, he saw quite a nice scattered angle of products, although most of it did still go straight through. And so the only way to explain this, he thought, was that if our atom was in fact not a mass like the raisin bread, but mostly composed of empty space, with the positive charge confined to the nucleus, a very small concentrated mass in the middle. And so now we have our picture of the atom that we're very familiar with. Well, this is more of the pop culture version, where we have a positive nucleus with negative electrons flying around. And of course, this is very, it's a, I guess, cartoon picture, because if you wanted to think of it in terms of real scale, if our atom was the size of a football field, the nucleus would fit, smaller than your fingertip. So that's where all the mass and the charge is concentrated. So what that means is that atoms are mostly made of empty space. And if we're all made of atoms, and everything is atoms, why is it that this empty space doesn't allow us to go through it. Why can't empty space overlap with each other? So there are a couple of reasons for this. The first thing is that matter likes to have structure. So, I mean, solid state matter. And there are stable configurations, and so they're energetically stable, such as this crystal lattice. Different types of materials will have their own structure and maintain that. So if I'm holding a piece of metal, the atoms in the metal will rather stick to each other than interact or bond with me. And that's natural. So that's why matter has very defined, stable structures. But that doesn't explain why we can't, well, not entirely why we can't go through it. So the answer lies in electromagnetic repulsion. So in this case, you can think of two magnets here. If we inverted one of them and we had the south facing the south, we know from experience that they're not going to want to touch. And that's the same thing as when we have two particles of the same charge. So if we have two positively charged particles, the closer we bring them together, the more the greater the repulsion between them. And so if you have two atoms, although the electrons are quite mobile, and in fact, the rearrangement of the electrons in atoms is what forms chemical bonds or allows us to have chemical reactions. But if you look at just the nucleus, the positive nuclei will not want to kind of collide with each other unless you have really energetic stuff like nuclear reactions. So that's basically it. There's no, the repulsion is so strong. But it's not just that. If we consider a more fundamental principle, and I won't elaborate too much because this will go into quantum mechanics, but the idea of the Pauli exclusion principle says that no two particles, no two, I guess in this case, two electrons can occupy the same space in the same way. So it can't have the same state. And if you imagine all these boxes being different states, something like having two pigeons in one is not possible. So when you bring two atoms close together, at some point, they will overlap with each other. And when you overlap, the electrons might want to share the same position, and that is not allowed. So basically, the reason why we can't walk into a wall is that the electromagnetic repulsion is so strong, and the Pauli exclusion principle make it so that you can't overlap atoms. So that's what happens when you try to walk into a wall. And when we actually make physical contact with an object, what we're feeling are the repulsive forces. And I can't talk about the nerve endings of our fingers, but really that's what's going on. And so that's why we can't walk through walls. But now I'm claiming that sometimes we can. And to understand that, we have to go into quantum mechanics. So we all know that light can sometimes be represented as a particle and sometimes as a wave. And this was something that Einstein worked on and a lot of other people. But in the early 1900s, the French physicist Louis-Philippe proposed that all matter could have a wave-like behavior. So that means anything with a momentum, a mass, a velocity, or energy of some sort has a wave property to it. Now the question really is, how important is this wave behavior and whether it matters at all? Well, it turns out this only matters for very, very small objects or very, very small particles traveling very, very fast. So if you take somebody like me walking at a normal speed, my wavelength is going to be on the order of 10 to the minus 34 meters, which is so insignificant that I'm basically a particle. I'm basically a solid object. But if you take an electron, and that at speeds that are normal in when it moves around the atom, now our wavelength is at 10 to the minus 10, minus 11 meters, or a nanometer. And here it does matter. So this is just an image published in Scientific America of a matter wave. But now if we have something like a barrier here, and we have a wave going to it, a particle would normally just hit it and bounce right off. But if we have a wave propagating, then the barrier will not stop it, but will attenuate it, so that if the barrier is thin enough, it can actually cross to the other side and have a non-zero probability of ending up on the other side. And so this effect is called quantum tunneling. And here's just a simulation of a wave packet of crossing a barrier. And you can kind of see the wave nature, the ripples, and a faint picture on the other side. So there is possibility for matter, when you think of it as a wave, to cross these barriers. Oh, by the way, for all the PhD students here, Louis-Philippe actually published this for his PhD dissertation, and it was only 18 pages long, and he got a Nobel Prize with that. So it's a lot of pressure for. Okay, so how can we use this? Well, it might seem like this is so small and insignificant that it doesn't matter to us in our daily lives. Well, we can actually use this phenomenon and create a microscope that that does exactly that. So if we bring a tip close enough to a surface, oh yeah, this is called scanning tunneling microscopy, and that's the area, that's the main instrument I use for my research. But if we take a tip and bring it close to a material, but not touching, and we leave a gap there, this vacuum, this gap, this empty space is like a barrier for the electron. There's technically no reason for the electron to go through that empty space. But in fact, we know that, I wouldn't be talking about this if it didn't happen, but the electron can tunnel through from the tip to the surface. And in fact, that would allow us to create images such as this and that. So the first image is taken by IBM, and where each of these little bumps is an actual atom. And we see that when we create a corral of cobalt atoms, you see the standing waves there. They've trapped some electrons from the surface. And so it's very nice because you do see the wave property, like the ripples on the surface of water. And the way I use it in my research is I take my tip and I can look at, so the image on the far side is one that I took in my experiments. I can actually see individual atoms and molecules on there and how they interact with each other, what it says about the properties of the molecule and the surface and everything else. And so using quantum tunneling, I can do experiments at a scale that people thought were inaccessible from before, because they just didn't know that we can actually see individual atoms. And so basically there you go, that's how sometimes you can walk through walls and sometimes you can't. But I hope I've convinced you that, in fact, when you're small enough, like an electron, walls don't matter as much. So, thank you.
So what I've gotten from that is that the boat is too big to make it through the...
Or not moving fast enough.
Yeah, oh, and not moving fast. Oh, there's an 8 km/h speed limit on it. So the other thing that I did when I was in the boat is that I read Thomas King's The Inconvenient Indian. Thomas King was a Massey lecturer a few years ago, and it was a history of Aboriginal peoples in Canada and the United States post-contact. And what was interesting to me about that, aside from learning an awful lot about it, is that just before I went away from here, I had a book of old photographs that I gave to another former assistant, and he went gaga for this book of photographs because they were mercury paper photographs. And he said that that was pre-contact. And I thought that the ideas of pre-contact and post-contact were in these completely different contexts, namely photography, pre-contact, that is pre-contact sheets, right? Contact sheets were the precursor to thumbnails, yes, in the digital world. And speaking of which, there's a lost positive, because if it can be a precursor, can there's a such thing as a post-cursor? Or just a cursor, damn it? Anyway, there was a precursor to the modern digital world, and this has very little to do with what Philip Sayers is going to talk about, except that it has to do with books. And I thought that I would just hang my hat on that one, because Philip is going to, his main area of focus is on contemporary fiction, and he's a first-year PhD student here with us. And his talk is Bridging Interests in American Fiction and Digital Humanities. And so perhaps you can let such more light for me on contact and books.
Thank you. Okay. I figure I should probably start by explaining how what I'm going to talk about relates to the theme of contact. Because the word won't really appear in much of what I'm going to say. Essentially, I'm using the word contact in the sense of our contacts, the people with whom we have contact with. I'm essentially talking about our wider social relationships, and specifically about ways of visually representing our social relationships. And the main way of visualizing social relationships that I'm going to be concerned with, I guess what you might call character maps, or network diagrams of characters in various novels. This is not a novel, this is from Hamlet. I have a few other examples. There's this one from the series of graphic novels, Scott Pilgrim. This one, yeah, this is from one of my favorite, maybe my favorite novel, Infinite Jest by David Foster Wallace. It's an 1,100-page novel, so hence you can see why there are as many characters there. They get even more complex than this. For example, this one is basically all the philosophers ever, essentially. I mean, it's a mess. It's completely incomprehensible. But you can kind of see that the big figures here: Aristotle, Hegel, Nietzsche, Marx, Kant. These are the figures who have lots of kind of links to other philosophers who, and essentially the number of links that you have is a fair representation of how much influence you have. So it's kind of useful even if it's a mess. Anyway, so just to give you a very brief overview of the structure of my talk, I'm going to be, in the first half, talking about some very basic ideas from network theory, basic because I'm an English student and I don't really know very much. And I'm going to be using these ideas to think about one novel in particular, a novel called A Visit from the Goon Squad by Jennifer Egan. It came out, I think, at the end of 2010. It won the Pulitzer Prize for fiction. It's really great. I would highly recommend it. Then in the second half of the talk, I'm going to be thinking more about the implications of using these types of diagrams to think about novels, but also to think about life, to think about how we interact in our social world. So, A Visit from the Goon Squad has kind of an interesting structure. It's in 13 chapters, and they're all very different in style. They all are told from a different perspective, but they do have links, as in, so a minor character in one chapter will suddenly become the main character in the next, or you'll have like a chapter narrated by a character who only just appeared very briefly 100 pages earlier. And yet they're very, very different in style. There's one chapter that is entirely written in the form of a PowerPoint presentation. And I think the interesting thing about this structure is that it kind of renders visible the complex interconnectivity of our social relationships, especially in a world where we have the internet and we have social networks and social media. And what I want to do is to kind of take further this making visible of social connections and represent them on a network diagram a bit like this. There is, in fact, somebody who's done this already. There are people who've done this about this novel just on the internet in a non-serious, non-academic way, but there is an academic writer who's thought about these kinds of diagrams. His name's Franco Moretti. He works at Stanford. He's kind of he's an odd man. His whole thing is, he calls it distant reading as opposed to close readings in the kind of standard way that all English students are taught to approach texts. His theory is basically, we have so many books. I mean, just the books in this library are probably a lifetime worth of reading alone. Nobody can read all of the books, and what we tend to read is just what gets put in the canon. So he says, well, why not just give up on the effort to read all the books? Why not let the computers read them for us and use this data set that we can put into a digital form to think about literature in very, very different ways. I think it's a really interesting approach, and he has a book called Graphs, Maps, Trees, where he he does this kind of approach to where he'll have graphs of, considering thousands of novels at any one time, which is, extremely different to what I spend most of my time doing as an English student. In the paper where he's talking about network diagrams, it's slightly different in that he is focusing on one work at a time. So it's not so much distant reading as a kind of middle distance reading. It's not close reading in the traditional sense, it's somewhere in between. So to give you a quick example of what he does, that diagram that I showed you from Hamlet comes from his paper. So it's essentially just any character who speaks to another character, they get a line drawn between them. And he looks at things like the amount of clustering. So here in this kind of, well, it's a pentagon but with 6 points. All of these characters, Hamlet, Claudius, the Queen, Ophelia, Polonius, and Laertes, they all know each other. They're all kind of mutual friends. So this is what he calls clustering. And if you compare this with Horatio, Horatio has just as many contacts, but most of them don't know each other. It's much more scattered. And he has an argument about how Claudius and the court, this represents one social structure associated with a specific historical period, and the Horatio represents the kind of incoming social order that's much more scattered and much more international. So if we apply this to A Visit from the Goon Squad, this is my version of this kind of diagram. It doesn't include every character, otherwise it would get too messy. But these are the main ones. What I've done is I've divided it up into two halves. And the novel does this. It has, the first 6 chapters are called Side A, and the next 7 chapters are called Side B. So it's kind of set, it's meant to resemble a vinyl album. And Side A takes place mostly in the 1970s, and Side B is mostly from the 1990s up to, it goes into the near future, into the 2020s or so. And there are very different structures for each of these sides. Side A, I deleted this guy because he's not very important. He comes back in Side B as more important, you'll see, but Side A is mostly, if we ignore Sasha, it's mostly characters who all know each other. It's a very clustered social structure. Whereas Side B is much more scattered. There's an increased number of characters. I think we've gone from 6 up to 10. But the number of links between them, as in these lines, has gone down. It's gone down from 12 to 11. And there are 5 characters, all these ones at the edge, who have only one link to the rest of the network. And I think you can make the argument that the reason for this is the impact of technology, both increased geographical mobility and the impact of the internet and social networking. And once you get into the 2020s, this guy Alex, the guy who I deleted from Side A because he's not very important then, but he comes back in Side B, and he has 15,896 friends. I assume friends is used here in a fairly loose sense. He has what the novel calls reach, as in he has lots of contacts. So at this point I'm going to kind of slightly shift focus, because I could carry on kind of applying what Moretti does to this novel, but I don't think that would be particularly interesting. What I think is more interesting to consider is the implications of thinking about society in these terms, in terms of a network. So if we think about this in relation to other ways of representing society, the ones that I have in mind, this is, I'm sure some of you may have seen this, it's the idea of the body politic. I don't know how visible it is, but all of the king's body here is made up of the subjects. And this is kind of a very common way of representing the social structure of the state in the, I guess, 16th, 17th, 18th centuries. And it has a very clear idea of hierarchy and class structure. And I guess another way of representing social relations would be a family tree. This is one from Game of Thrones. No. I guess what's different about the network diagram is that whereas these have a very clear idea of power structure, of hierarchy, the network diagram doesn't seem to. It seems like everybody's on the same level, that everyone's, and there's almost this utopian sense to it, that everyone's connected and everyone's mutual friends and etc. And it seems to erase these power structures. I don't think it actually does erase the power structures. What I would argue is that it sets out a different type of power structure, a power structure that isn't so much based on what class you were born into, as in the body politic, or what family you were born into, as in family trees, but more power based on what the novel calls reach, how many people you know, how many contacts you have, how many contacts your contacts have. It's essentially the whole networking thing that is awful. But anyway. I think as well as setting up a very different idea of power structure, I think that thinking about networks as a way of envisioning social relations entails a very different view of subjectivity. By that I mean, I guess, a different view of how we exist in the world in relation to other people. This is a quotation from a review of the Franco Moretti book that I was talking about. I'll just read it aloud. The idea that data is gold waiting to be mined, that all entities, including people, are best understood as nodes in a network, that things are at their clearest when they are least particular, most interchangeable, most aggregated. Well, perhaps that's not the theology of the average lit department yet, but it is surely the theology of the 21st century. I'm not entirely sure how I feel about this. There's certainly something scary about understanding people as nodes in a network, but equally I don't want to turn this into an anti-Facebook rant. I think there is, however we feel about it, something quite accurate about the idea of people being viewed in this way. And I think it depends. I think that the subject, the sort of subject that emerges from this viewpoint is a subject that is defined by what Jennifer Egan, the author of the novel, calls the fetishization of connection. And to quote from her, she says, "Who cares that we can connect? What's the big deal? I think Facebook is colossally dull. I think it's like everyone having to live in a huge Soviet apartment block in which everyone's cell looks exactly the same, and we tolerate these horrific aesthetic conditions in which people change around our artwork and move our furniture when we're not home because we want to be connected. I think it's madness. I mean, I'm on there, how can I not be?" Like Egan, I'm on Facebook too, so I think there are clearly benefits as well as costs to being in the network. But I do think it would be worth considering perhaps more seriously the question that she asks rhetorically, as in, I'm on Facebook, I'm in the network, how can I not be? Are there ways that we can kind of opt out of the network? I think I'm just going to end by going back to the novel and reading a short paragraph, which I think it's a bit frivolous, but I think it asks some interesting questions about the future of social networks and also the future of how we study them, and kind of opens up some interdisciplinary questions that seemed appropriate for this event. So this is the quotation from the novel. "No one says viral anymore," Lulu said. I mean, maybe thoughtlessly the way we still say connect or transmit, those old mechanical metaphors that have nothing to do with how information travels. See, reach isn't describable in terms of cause and effect anymore. It's simultaneous. It's faster than the speed of light. That's actually been measured. So now we study particle physics. Thanks.
about 11 things there. I was thinking, oh, gosh. Meanwhile, while I was on the boat, I wasn't thinking anywhere nearly as smartly as well as you guys tend to. Again, on the theme of contacts, there was an emergency switch on the boat to break electrical contact to shut the motor down in case of an emergency. And I began to think that contact is not just in terms of electricity. Without contact, you can't have electrical flow except in arc welding or carbon arc lights or lightning. I understand there was a big thunderstorm here a few days ago. But we actually need actual connections, and the question of whether Facebook is an actual connection or not is, I don't, barely up for debate, except among 17-year-olds and the 14-year-olds in the world. But I got to anyway. I was just thinking about that as contact, which is connection and connectedness. And I also knew that by now I would be thinking that my dear wife would get here sometime soon, and I would start getting antsy because I haven't had any contact with her in 2.5 weeks, and that's way too long for me. So if a woman walks in, I just jump up and, you know, it's a desire for contact. In the meantime, which gets us around, I suppose, to health, doesn't it? And Sabrina is passionate about improving the healthcare system through interdisciplinary collaboration. Began working in healthcare engineering in 2008 at the Center for Research in Healthcare Engineering, and completed projects on H1N1 pandemic planning and process development. Her master's degree, this is after a BA in Industrial Engineering, pursuing a Master of Health Science in Clinical Engineering. I mean, these are all concepts that I can't put together conveniently and easily. I'm a very simple sailor here. But she is working in Saskatchewan on resource utilization and identifying opportunities to improve efficiency and access, which I understand is the subject of improving Canadian healthcare. There you go.
The middle button?
No, the one on the right.
Just one on the right? Okay. Good to know. So yeah, I'll be talking to you guys about hopefully just one way we can improve the healthcare system, and particularly in the emergency department. So if we can have just a quick poll on who has waited in the emergency department. Okay, so one person hasn't. That's impressive. So I think most of us have had contact with the healthcare system through the emergency department. So I'm going to be going through the example of what happens in the emergency department. Basically, why do you wait? And also the tool of discrete event simulation is sort of helping us look at these processes and how we can hopefully reduce these wait times and improve healthcare. So you're a patient in the emergency department, and the general process you go through is, well, you're entering the emergency department, you're getting triaged, then you will wait, you enter the room, you see a doctor, you get your blood test, and then you're discharged. So this process in and of itself is not wrong. Everything is there for a reason. But the real question is sort of what happens in between all these things. And so between all of these events, you're waiting, in essence. And so the question is, well, why are you waiting? And so let's, for a moment, look at how the physician views things, because they're one of the key determinants of actually how long you wait. And so usually what happens is that they go through the patients in order. So in this example, there are 3 patients, and so he sees patient 1, then he sees patient 2, and then he sees patient 3. He then checks the blood result of patient 1, then sees patient 2 gets discharged, and patient 4 enters. And then he checks the blood test for patient 3. So that's sort of generally what happens. He sort of goes through the patients in order. But as you notice that there's the blood test factor, and it takes a time to process this blood test. And so the way that works is that the doctor enters in the order, the nurse and phlebotomist draw the blood, it then goes to the blood lab, usually called clinical pathology, to get processed, and then your result gets entered into a computer, and the doctor checks this computer and makes a decision based on the blood test result. So let's go back to the physician for a moment. And he goes through a similar process where he goes through each of the patients in order. And there was observations done to show that this is actually a somewhat valid assumption. So he goes through patient 1, 2, and 3. He does a procedure on patient 1, and then patient 3 blood test is ready. And then, because he's going in order, he continues to patient 2, checks the blood for patient 3, realizes that the test results are there, and now proceeds to meet with patient 3, and now patient 4 can enter. And so, basically, patient 3 could have been discharged earlier. And patient 4, therefore, could have entered the emergency department earlier. And so, therefore, patient 4 is technically waiting in a necessary amount of time. And this actually has been, in terms of baseline statistics at Sunnybrook Hospital, they determined that this was actually 3 hours of extra waiting alone. So the one step of the time between when your test was ready to be seen, between when the doctor actually saw it and made a decision, is actually 3 hours on average, with a standard deviation of 2 hours. So like up to 5 hours without seeing the blood test when it's ready. So I mean, this is clearly a huge factor in how long people wait. And so, why did the patient wait so long? So was nobody working? Well, no, they were all working very hard, actually. The doctor didn't take a break. The nurse sort of did what she was told. The lab processed as quickly as possible. Usually emergency department blood tests, they get priority, so they're done within 45 minutes or so. And so the reason why you wait is probably just because people have problems with their processes, and they need help figuring out how to make those processes better. Okay. And so tools can help them do that. So for the rest of this presentation, I'll be talking to you about simulation modeling, and in particular discrete event simulation modeling, which is one of the key tools that we use in engineering to say, well, how can we improve the healthcare system? And so simulation, I asked people what they thought of it, and they came up with flight simulation, which is actually not a bad sort of analogy, in that if you're in the simulation model, why do you want to use it? It's because it helps you look at the real world, and the real world has variation in it. And so you want to be able to capture the variation in your system, and in this case, the variation in the healthcare system, so that when you have solutions, you can see whether or not they'll work, taking into account all the variation in the real world. And so discrete event simulation modeling is very good in hospitals because there are lots of processes. You're dealing with large volumes. So Sunnybrook Hospital, I think, has 1.2 million patient visits a year. And if on average each of those patients has 5 blood tests, which is not uncommon, I'd say, that's millions of blood tests. So this is a large amount of data. There's significant variation. So whenever you're dealing with so many people have lots of variability, and so that adds significantly to the complexity in your system. And you're dealing with many scenarios. So there are many illnesses, and there are many treatments, and there are many just different types of patients from age and demographics. And so simulation allows you to test solutions. And this is different from basic statistics, which can evaluate solutions and identify problems, but it can't actually tell you if a solution will work. And so by testing solutions, you can eliminate sort of some of the issues with implementation and see which potential idea is better. And so examples of how this has been used in healthcare is one, patient flow and appointment scheduling. So Ontario has one of the best cancer survival rates in the world, and that's partly because they actually do a lot of simulation modeling. So the time at which you get your screening to the time at which you get your treatment procedure was all modeled, actually. That's a huge part of why. So like the US, for example, spends more on cancer care, but actually does not get as good results. Canadian Blood Services. When you walk to the hospital, you want to know that the blood that's there is of your blood type, and that they have it available, and that it's as young as possible, I guess. It just has not been sitting there for a while, because then the efficacy decreases. So simulation modeling was used by Canadian Blood Services. It's being used in emergency department wait times, staff scheduling. So do you have enough staff such that at the peak point in your emergency department, you're hopefully waiting as little as possible. And then also used in surgery scheduling resources, so making sure that the surgeon actually has the resources available to do his surgery. and also the upstream and downstream consequences. So if you do certain types of surgery at one type of the day, how does that affect you later on in the day, basically? And that's been done at most of the top hospitals in Toronto, so Mount Sinai, Toronto General, and St. Mike's. And so, in order to really explain discrete event modeling, I really have to talk a little bit about probability and statistics. And so, histograms are basically bar charts. So the higher your frequency, the higher your bar chart. And the larger your sample size, the more likely you are to see a trend. And so you can kind of see that as you have more lines and more samples, that this trend of this sort of, I guess, hill takes shape. And that is sort of what we call a probability distribution. So in the center, or like the things that are sort of higher, are more likely to happen. And these are your high frequency events. And on the edges, you have your rare events, so things that are less likely to happen. And so it's important to understand the sort of variation in the system and these sort of high frequency and rare events, because you can't really use averages sometimes. Averages are misleading. So this is a graph of healthcare spending. And so if you were to take the average person, they only contribute to $181 per person. And so if you were to base all of your healthcare spending on the average, we would not be spending very much money in healthcare. So in this case, we have the top 5% of the population taking up 80% of the resources, and that's often a quote you hear. And that's because sometimes the people who are less frequent take up a disproportionate amount of resources, and therefore we need to simulate to account for sort of this variation. And so, taking this back to the emergency department, every single step in this process has variation. And so simulation allows you to look at the variation in each step of the process, and then how do all this variation, how do they interact, is essentially what it's doing. And so this is an example of a simulation model. And so on the top, they're actually modeling the current process in an ophthalmology clinic. And so the reason why you model the current process is to validate it. So you actually match what happened in real life to what's happening in your model, and you want to know if you're able to get enough of the variation to have it make sense. And so the idea is that in your future model, you're going to change something in your simulation. And then because you validated it, you know that it has captured enough variation such that when you test this new solution, the results that you get should be able to tell you what will happen when you decide to implement it. And then this is an example of actually from my lab of Toronto General Hospital. It's not completed yet, so I can't tell you how well it worked. But this is all the operating rooms and all of the post-surgical wards. And so basically patients are arriving on the top for their surgeries. They're having their surgeries over here in the operating rooms, and then they're being taken care of in the post-surgical wards. And so they're mapping all of the scheduling, all of the resources that are required to make this happen and make this happen as efficiently as possible. And so if we take this back to the emergency department, how does simulation help us in this scenario? And you'll remember that the blood test was a huge problem. And so you can actually simulate, well, what happens if the doctor found out about the blood test sooner? And so currently they're actually, and you could potentially save, those 3 hours. And so they've actually done a pilot test in Sunnybrook Hospital with this thing called a push alert system on an iPhone, which actually tells the doctor when a blood test is important and that they should act upon it. So they don't have results for this yet, but you can imagine that there are large impacts to this. Simulation models also used in pandemic planning. So if you were to simulate the emergency department, the first place where people would say H1N1 enter is the emergency department, because they're like, oh, I have a flu, and then they go in. And if there's a pandemic, you have a high increase in your admissions for flu. And so you can sort of model, well, what happens if you have a lot of patients, a few patients, and very few patients. So you can model different scenarios of a pandemic using simulation modeling and say, well, how does that impact how long they see the doctor, how does it impact your blood test, and how does it impact your discharges? So there are many different scenarios that you can test on a simulation model, and you can choose, well, what should we do in certain scenarios, and maybe for our current situation, which solutions work better than others. So in conclusion, emergency department wait times can be reduced if you break down the system And one method is through simulation modeling, and that's because you're able to account for a significant amount of variation in the system. And you're also able to test the solution before it's been implemented. So you don't disrupt the system, you don't lose the goodwill of people in the system to try different ideas. You also don't hurt patients in the process of running this simulation in the computer to see if a solution will work. Thank you.
What did you guys get out of the other lectures? What was your common thread of the other two, et cetera, et cetera? Or was there one? Or are you just so glad to have it over with that you're not even thinking about these things?
Well, I can start. I found it interesting when in your talk, Sabrina, kind of similar types of network diagrams were used. And I guess because as an English student, I tend to approach things critically to look at what kind of assumptions are at play and what kind of ideologies and what kind of bad things might be lying behind these ways of thinking, which tends to blind me somewhat to the practical uses of things. And I guess seeing the kind of practical uses to which these types of diagrams are put in your talk was eye-opening.
Thank you. I also never thought of literature that way, in terms of networks of people, although it makes sense now that I think about it. Yeah.
And I guess chemical bonds are basically, I mean, in solid state physics, you have different crystal structures because of different types of bonding, and depending on how the arms are stretched out, you get different, I guess, networks. Like, so the same thing, carbon can form either graphite, which is pencil lead, or diamond, which is much stronger. And it's just a matter of how the bonds are being arranged.
Well, and it's also a matter of some sort of probability of certain things happening depending on conditions, though. I could be wrong.
No, sorry.
Like, different states happen as a result of different conditions, and there's sort of a probability in which they happen based on those conditions.
Yeah, you also need to overcome some type of energy barrier or something under certain circumstances. High pressure, high temperature is often a catalyst for,
High temperature and high pressure work perfectly in novels too. Speaking of which, in plays there are all those kind of charts in addition to character who knows whom. There are also things like the costume breakdown. Who's wearing what when? And if they're wearing costume A in this scene and costume B in the next scene, what's the time lag between them? And how many people they have to in order to get the quick change done? And then, where's the prop that they carried off on stage right, and when they need it again, and it's all these mechanical things, so it's modeling in advance. You cannot waste the time of the director and the actors in the rehearsal hall, let alone in the theater, which is a really expensive place to work. Trying to figure out where the prop ought to be in order to be where it needs to be in the next scene. You've got to have all that charted before you can cast the show. So any other,
Thank you. See one of the presenters. I'm wondering if all three of you, looked into the what's it called, complex dynamics system, which is the newish theory which looks at the models that are not predictable and scary, and especially at things like predicting the weather when we can't actually predict. We're modeling, but we can't predict. And I'm wondering if that could be an interesting way to go. Not so much for literature, because you have a book and you can't add characters to the book. And you kind of know where it's going. But with hospitals, I think it might be very interesting to look at where your predictions might be wrong. Or like in situations like the virus thing you mentioned before. You never know what's going to happen. You don't know what the virus is going to do and how fast it's going to spread and stuff.
Sorry, I think I might have missed the question.
So the question is, have you looked at the complex dynamic systems theory as a possible way of modeling?
And so this complex, sorry, I haven't heard of it before. Okay. So it's just saying that there are things that we don't know that might happen?
Yeah, they try to model, but they can't figure out. If somebody knows it better, because I'm not in physics, but maybe
I was
okay, you can go for it.
I mean, are you thinking, so I think we're trying to ask about is more chaotic systems.
Yes.
So, I mean, that's what we have in real life. Everything has, we have so many degrees of freedom, so many parameters. There's the common butterfly that flaps its wings and then causes a tornado on the other side of the earth. So there is actually lots of modeling done on this. These are complex systems, but there are two categories. There's deterministic and there's non-deterministic. In the first case, if you are able to actually tag every single parameter, as many as you can, there are ways of predicting the behavior. And of course, in the other one, there's a famous double pendulum that if you swing it, the behavior is so erratic, and any movement of air could change that. But there are ways in modeling, and I do a lot of simulations for molecules, of accounting for that or taking approximations of stuff. And in most cases, I mean, especially if you're talking about large average behavior, the central limit theorem does apply, so the standard behavior. So we don't actually care about the tail behavior, but most average common outcomes is what we're interested in. If that answers your question.
So I guess to sort of answer your question, a lot of things that we do in sort of simulation, especially more statistics-related simulations, is that you always say you're 95% confident, and so I'd probably all the things that you don't know are going to happen sort of fall in that other 5%. So that'd be my short answer to it.
Yeah.
I have a question for Sue to follow up on that. So you're looking at something very micro, where you look at quantum chemistry, but also so in terms of your simulations and your dynamic simulations, do you look at quantum theory or do you look at more molecular and atomic?
So actually, right now it's kind of interesting. So for the past few years, I was working mostly quantum chemistry. We're dealing with a couple of atoms interacting with a few more, and really we want to simulate every single electron that's in there. So we can't do more. We don't have the computer resource to do that. But there are techniques to use quantum chemistry and apply molecular dynamics, which is more of a classical theory of treating things as balls rolling around rather than as waves. And so there are ways to combine them in an efficient manner, but only for small systems. And surprisingly enough, they do give a very good qualitative behavior, not necessarily quantitative.
Yeah.
Another question. So for Sabrina, how can big data impact simulations? So using large amounts of data about populations and patient data and
I guess it really depends on what the big data is of.
Or just in general.
So, because otherwise it sort of applies very broadly. So I think IBM's Watson, for example, is looking at how do you predict what the treatments might be and all the diagnoses. So I think that is a function of big data and being able to be more targeted in your care and being able to predict later on what you might do with it. I know it's sort of, that's a good example. I guess this is not exactly big data, but I know that machine learning has been used for emergency departments actually. Machine learning expert over there. And that's because the different emergency departments sort of, as people come in, it sort of learns what the general trend is as a person goes through the hospital, and so it tries to predict the resource demand as a result of these people entering the system. And so in sort of what I use, it's sort of all predetermined, all your parameters are preset, and a person would have to manually go in and reset those parameters if things start dramatically changing every few years or so. Whereas in a machine learning model, it would say, well, how will these parameters update on their own as a result of knowing how the people coming into the system are changing.
Yeah.
Question for Philip. I was sort of intrigued. It's pretty cool to hear about academics in English worrying about studying the canon in sort of an automatic way. That's really interesting because that's how I often treat the data that I think about it. And we do think about language, and there are some people that do, but also images. And what's really interesting is that when we apply some of these models, we discover things we didn't necessarily expect, but might make sense in hindsight. So for example, if we apply some of our models to images, we find that it pays attention to sort of the, a lot of these models create these frequency filters that notice edges in images, and that's a really obvious thing to do. And well, it turns out that the human brain does similar sorts of things. So I'm wondering what, and this, I don't know how much experience you have with this side of academic English, but what has for you been the most interesting thing that was revealed about the canon that you might not have noticed if you hadn't done this sort of automatic?
I guess the first thing that comes to mind is the Stanford Literary Lab that I mentioned. They publish a pamphlet every few months. The paper that I mentioned was the second of these pamphlets. The third one has to do with the author that I mentioned as the guy who wrote my favorite book, Infinite Jest. This paper is about the process of canonization as it happens through Amazon, and how essentially when you click on a book's page, you have customers who bought this also bought. And there's a paper that is essentially analyzing how it looks at this book, Infinite Jest by Wallace, and looks at the books that customers bought when they bought that. And what he found is that it tended to be a lot of other epic canonical works, so Moby Dick or Ulysses, all of these big doorstop novels that are part of the canon. And this, by seeing how people associate this novel, this kind of illustrates in a very kind of quick and visible way how works become part of the canon and how people associate them with other books. So, yeah, that's the first thing that came to mind.
Because this is the first of these I've ever done, is this a hard and fast we have to keep talking until we reach 9 o'clock, or do we, my brain is certainly full, aside from it being 10 to 3 in the morning, Swiss time. And so on, going once, going twice. Sold. Thank you very kindly. This has been a terrific evening. And thanks to you guys for organizing these.
Thank you.
This is excellent.